Okay, hello everybody and welcome to this week's video. My exams are finally over, so I might have slightly more energy than in the last 3 to 4 episodes, the last few videos. Anyway, today what we are looking into is Lie groups. We will probably focus on Lie groups and then some Lie algebras today, and this is one part of a two-part series because I am quite tired from my exams, so I can't go through all of it in one. But that's okay, let's get right on with it. So, well, I'm surprised I haven't really talked about these before. They're kind of a really key mathematical construct to understand for most of physics. I guess the first time they kind of pop up is Noether's theorem. I have no idea how to say it. But to do with parity. Um, and that guarantees a conserved quantity. Um, Whenever a physical system possesses continuous symmetry. Um, and how do we work with these symmetries? Well, we do that through Lie groups, continuous symmetries, that is. Well, basically, I aim to build this theory up from scratch, so I guess it's not really a derivation as such, but that kind of understanding. Now, there is certainly a OneNote thing, which is my pen has stopped being able to scroll. So I will be using the mouse cursor to scroll, but this will slow me down significantly. So I'm very sorry. We will find out shortly as to the extent of which that hinders me. Anyway, I'm sure anyone who's bothered to click on a video about Lie groups and Lie algebras has some understanding of group theory. Regardless, I'll just give a brief overview of group theory. So if we have a group G1, which is in a set, which is rather a set G, with a binary operation satisfying 4 axioms. So we have closure, which is G1 dot G2 is in G for all G1, G2. That looks like a Q. G2 in G. And then associativity, which is that G1 times G2 times G3 is equal to G1, G2, G3. Identity, we have an element E in G, such that E dot G is equal to G dot E is equal to G for all G. See, that's what I mean. I was trying to scroll down there. And then our final axiom is inverses. So for every G in G, there exists an inverse in G, where G times its inverse is equal to our identity element. And these are our 4 laws of groups. So we have closure, associativity, identity, and inverses. This is just a quick reminder. Now we kick it up a notch, so to speak, with Lie groups. So a Lie group is a group G. I'll pop a little thing there. So a Lie group. This is a group G. That is simultaneously a smooth manifold. So group multiplications and inversions are smooth maps. So the idea here is that group elements depend continuously and differentiably on parameters, which is what allows us to differentiate. Because I mean, how on earth would you differentiate a group then? So that's the kind of premise of the whole thing. So we have that it's a group, but also a smooth manifold. such that group multiplication and inversion, I'm not going to write that actually, and it's they group elements depend depend continuously and differentiably on parameters. Okay. So we kind of deal with two important ones. They're matrix Lie groups in QM, quantum mechanics. I'll just probably call it QM for most of this video. So in QM we have three main ones, which is I'm going to do triangles. SO. This is our real, so n by n. They're orthogonal even matrices with a determinant of +1, and these give us our rotations in Rn. Lead to rot Rn, and that should be reals. How do you draw reals again is the question. That'll do probably. And then we have U. This is a capital U, to be very clear. This is a complex, so complex n by n unit matrix, such that U transpose times U is just the identity. And then finally we deal with SU. SUN, which is a unitary n by n matrix with determinant being equal to 1. And these are the three main ones that we deal with. A group element, depending on a continuous parameter theta, defines a smooth curve g theta which goes through this group, and g of 0 is E at the identity. So yeah, that's kind of the Lie groups that we'll be dealing with and looking at on a very surface level. Let's look at, well, I guess we'll start to talk about Lie algebra. So the kind of theory, the central theory that we have is this: near the identity, any Lie group elements can be written as an exponential of some simpler, flatter object. That is an object that is flatter, like as a manifold. We can extract that by differentiating along a curve at the identity, and we will get a resulting vector space from that, and that is our Lie algebra, is that resulting vector space from differentiating along curves. So I'll write that down. Lie algebra is actually, I'm not going to write down the definition because it's probably easier to demonstrate. So let's take SO2 in theta in the regular, SO2, we have R as a function of theta, that's the rotation by some angle theta. This is a fairly well-known 2x2, cos theta, sine theta minus sine theta and cos theta again, and of course if you were to plug in various things you'd see how this simplifies down. Now let's do what we said and differentiate. So the identity element here is going to be R of 0, and we'll call this is I2. And to evaluate at this to actually find out what it is. Oh, I can't scroll down with the hand, can I? Because it doesn't show up in full screen mode. To actually evaluate what this is, we will simply differentiate. So this is going to give us our generator, which is J. We can actually, I should probably say this is equivalent to dr d theta at theta equals 0. Which is minus sine theta cos theta minus cos theta minus sine theta. That sounds right, at theta equals 0. Which is simply 0, 1, minus 1, 0. Okay, so the claim is that our full group element is recovered by then exponentiating our generator. Which is to say that r of theta is equal to e to the theta j. This would then, well, this is our exponential map, but this is just a claim at the moment, so let's verify that. Well, we can expand this with the Taylor series, so e to the theta j is going to be, that wasn't a very nice sum from n equals, that's not much of a better one, but it doesn't matter. And then that will be theta j to the n over n factorial, yeah, that's right, which is just I plus theta j plus theta squared j squared over 2 factorial plus cube j cubed over 3 factorial, etc. Now we can compute these powers of j squared, j cubed by matrix multiplication. We will end up with j squared being minus 1, 0, 0, minus 1, which is just minus I. And then j cubed is going to be, because I is just our identity, it's just going to be that times j, so that's going to give us minus j. J to the 4 is going to be that squared, which is just going to be I. J to the 5 is then going to be positive j. And you can see how we start to have a symmetry here. So it's going to be j minus I minus j, I, j minus I minus j, I, j. So we have a 4-periodic function. And we can sub this into our Taylor series from before. So e to the theta j, we're going to get theta to the 0 over 0 factorial I, and then theta, oh sorry, that should be plus theta to the 1 over 1 factorial j, and then it's going to be minus I, and then I forgot about the 0th term, by the way, sorry, above, forgot to mention that, over 2 factorial minus I, plus theta cubed. I'm just going to write this one and then I'll stop. What am I doing? Dot dot dot. And we can pull out all the I dependent terms. It's going to be 1 minus theta squared over 2 factorial. It should be all even powers with alternating plus and minuses. It would be minus dot 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 plus j, and then this is going to be our odd terms with alternating plus or minuses, plus theta to the 5 over 5 factorial minus dot dot dot. And we can expand this out, or rather we can this is, what am I saying? This is cos and this is sine. I hope that's fairly obvious through that Taylor series. So this is I cos theta plus j sine theta, and we can expand this out through the matrices. So this is going to be 1, 0, 0, 1 cos theta. It should actually be the other way around. Cos theta 1, 0, 0, 1, because stupid linear algebra. Sine theta is going to be 0, 1, minus 1, 0 for j. And this, of course, is then going to be cos theta sine theta minus sine theta cos theta. and this is r theta, which is what we attempted to verify. Okay, so we've so far established that for this SO2, our rotations on our plane, if we differentiate our theta function, r with respect to theta, r with respect to theta, then we get our generator function, and exponentiating the generator function will return us our original function. Okay, so this is kind of a fundamental idea of Lie algebras that's really important to understand, and we can generalize this. So if we have a Lie group, we have a group G with dimensions n, there's going to be n independent generators, so we can call those T, A, and that will be bounded a equals 1 all the way up to n, and we can get that by differentiating along each independent group. So we can define TA as dg d alpha to the a, where alpha equals 0. Yeah, alpha equals 0. Unhelpful symbols in my notes. And here just alpha to the a are group parameters upon which these derivatives are dependent, of course, by definition. These generators then span a vector space, which is called our Lie algebra, and it is the fancy Gothic G, which I'm not quite sure. I haven't actually thought about how I'm going to draw that. I want to have people how to draw Gothic G maths. Is it even called Gothic? I always thought. Yeah, how does one write Gothic letters in handwriting? Tend to write them in a sort of angular cursive. Oh, I like that. So how's that? It's like, okay, cool. So I'm just gonna do a box. That's gonna be my Gothic G from now on. So now we have a Lie algebra G, which is T E, where E is our element, times G. Now, generally in physics, we tend to include a factor of I in our exponential map from before, which is where you see e to the I thetas popping up a lot in QM, and also in other parts of physics, generally representing derivatives, and such. This is so that generators of unitary groups are Hermitian. Hermitian, yeah. So we can then, we have that U alpha is, I'm going to write exp because I'm a physicist, not a mathematician. I alpha, and then we're going to have, it's an alpha up there, T, and then an A. No, it's alpha to the A, and then T sub A. And then, of course, we have the T transpose sub A is just T of A. And that will be repeated over our index A. So unitary is then just automatic. If TA is Hermitian, then this whole transpose, we can actually verify this. So e to the I alpha to the A T sub A transpose is e to the minus I alpha to the A T, and then of course we know about this, so this is going to be e to the minus I alpha to the A T sub A, which is just e to the I alpha to the A T sub A to the minus 1. and then hence I group U transpose times U is equal to I. Thus it is verified. SO2 is a real group, which is why we wrote it without an I in the exponent, and that's my excuse. We will always use this convention of writing our exponents when we move on to complex unitary groups. But by definition, well, no, not by definition, actually. Anyway, I believe, by the way, that this is special ordinary, this is unitary, and this is special unitary. I realise I haven't pointed that out henceforth. The last thing I really want to touch on today is the Lie bracket, and then structure constants. And you may hear, or you may have seen, or have I done anything with this? You may know find structure constant and other structure constants and such. This is where they appear. Anyway, for matrix Lie groups, as we've kind of been focusing on so far, the natural product on the Lie algebra is the commutator. So if we have this TA, TB, where these are two Lie algebras, then it's TA, TB minus TB, TA. And this is our commutator. Now, we have a fundamental theorem in Lie theory which states that the commutator of any two algebra elements is again in the algebra. And that kind of derives then from our group ideas from up here, where we have that the product of any two must be in our group. Same kind of idea. As you explore abstract algebra, you find that you're just rewriting things but with different names, and they're useful for slightly different parts of advanced physics. I know I'm going to annoy all the mathematicians by saying that, but it's true. So since TAA is a basis here, this result must be a linear combination of basis elements for that fundamental theorem. So we can write this as I F sub AB to the C. Yeah. F sub AB C T C. Which is just summing over C. And now we have this real constant FAB to the C. And these, or rather, we have multiples of them. Those are the structure constants. They're antisymmetric in AB, and they completely sort of characterize this Lie algebra. Two Lie algebras are isomorphic if and only if they share the same structure constant. So comparison of structure constants is a very useful method for quickly comparing entire Lie groups or Lie algebras. We can take a physical significance from this as well, because if this is equal to 0, then we have compatible symmetries, and observables can be simultaneously diagnosed. But if that's not 0, then we have fundamentally related symmetries. And I guess this is where the uncertainty principle comes from, actually, come to think of it. Would be from here, but I will save that for the future. This brings me to the end of this first video on Lie groups, Lie algebras. So I even wrote a recap summary because I knew I was going to be too tired to do the whole thing, so I thought, let's do a recap. The Lie group is a group that is also a smooth manifold. So it depends differentiably on parameters, as we've sort of shown. And then we have our generator along a one parameter curve, like g of theta. That's the tangent, the identity. So we have that t is equal to dg d theta, that's our generator. The exponential map, which is our u, or rather e to the I alpha a to e to the I alpha to the a t sub alpha, that reconstructs our group elements from the generators as we've shown. We showed that for SO2, and then we have our structure constants which encode the algebra through commutation, as we have our commutative methods. We'll look at SU2 to find out more about the Pauli matrices next time. And yeah, we'll show that we get angular momentum algebras from that, with some h bars and some epsilons and some other things. But yeah, I'm gonna pick a slightly more important formula to end the video, or maybe we can do this one. That's a fairly important video. Fairly important thing to end on. And with that, I hope you enjoyed, and I'll see you next week. Bye bye.